Okay, hi again. This video is going to be on how we can create magnetic fields using electric currents. This was first discovered, as I mentioned in class, around 1821, I believe, by a professor, kind of like me, a physics professor, who was kind of like me, a little messy, a lot of wires lying around. I'm going to come down here. He might have even had a compass that looked kind of like this sitting around. And he also had a battery, I guess, and some wires, and things got messy. And what he noticed was this. At one point, I think this was even during a lecture, he did something like this where he shorted out his battery. And when he shorted out his battery, let's see what happens to the compass needle when he did that, when the wire was nearby. Notice how the compass needle moved? That was really exciting, because up until that point, there was no known connection between the current that you're going to get from a wire and a battery and the magnets which are associated with the needle of a compass. If you didn't know it already, the needle of a compass is actually a magnet. In other words, if I took this magnet, this bar magnet here, and suspended it by a string, that bar magnet would align itself such that the north was pointed towards the North Pole. That's how compasses work. Which actually means that if this is a North Pole, that the magnetic north is actually a South Pole, which is what it is. So it's a little bit confusing, but we call it the North Pole, but what we call a magnetic North Pole is actually a magnetic South Pole, because the magnetic north of a little magnet will point to it, and it'll only point towards the South Pole. It's attracted towards it. Little side, that was a little bit of an aside, but I wanted to let you know that. Anyway, that discovery by Oersted was a big one, and it led to a number of other discoveries, including one I'm going to show you right here. I'm going to go like this. Change my computer here, the orientation, so that the camera is looking at my whiteboard, and I think it's gonna work like this. So what I have over here is I have my battery. This is a 12-volt battery, one of the ones from the solar kit. Up here are some magnets wrapped in tape to hold them onto my whiteboard. These are the strong rare earth magnets. And then I have a very thin wire going from one lead of the battery. It's attached here to another wire down here. Let's see, rings attached. And that wire wraps around here, and it goes near the magnets right there. And it comes all the way around to this other connector and this yellow lead here. And watch what happens to that wire when I short out the battery. I don't recommend doing this often or at home or anything like that, but I'll do it very briefly. And watch what happens to the wire up there. See a small movement whenever I touch it. So what's actually happening is when I connect the system up like this, there's a current that's running through this wire. That current is actually generating a magnetic field, because that's what currents do. That's really what Oersted discovered, that the currents create a magnetic field that affects a compass needle. But the magnetic field also, it's interacting with the magnetic field from this magnet here. And it's basically causing the wire to move as a result of that interaction between those magnetic fields. This was a really big deal. This is telling us that as a result of a current flowing through a wire, we are creating a magnetic field. Huge discovery. This is the discovery, essentially, that led us to the creation of motors, eventually, and before that, electromagnets. And what happens is if you generate a magnetic field around a wire, I'm going to show you what the magnetic field looks like. The magnetic field lines are different from the electric field lines. In a magnetic field, let's say there's a current running through this red wire right here. You can see the red wire. Can't tell it. You can see that my picture of myself is really small. But in any case, if there's a red wire here, the magnetic field, if the current's going this way, the magnetic field actually wraps around the wire like this. So if you could put it through the lid of this that I used to put on top of the other magnet earlier, and put some iron filings there, the iron filings would create basically concentric rings around the wire, illustrating that the magnetic field lines are actually circular around the wire like this. They're strongest closer to the wire, they're weaker further away, but they wrap around the wire. And the direction that the magnetic field lines go, because they actually have a direction, magnetic field is a vector, kind of like the electric field is a vector, would be if you use your right hand and you point your thumb in the direction of the current, your fingers wrapped around the wire illustrate the direction of the magnetic field that it would be pointed around the wire. So that's a huge discovery that was made. And if you want to get a stronger magnetic field as a result of an electric current, here's what you do. You actually create a coil like this of the wire. I'll wrap it around my finger here. Then when you run a current through it, the magnetic fields actually reinforce where my finger is, going through the coil of wire. They're really strong in here, and they're weak out here. We'll talk about this more in class, but it's pretty fascinating that if you create a coil of wire like this, should be a nice clean coil actually, it would look better. But if I were to create a coil of wire, magnetic fields, as they wrap around each strand of wire, they reinforce each other in the middle here, in the hole of the donut, so to speak, and they basically get really weak out here. It's kind of like two plates. It's actually the magnetic analog of the electric field between two plates. As a result of that, you've probably seen these. This actually is something I took out of an old washing machine that we had that the motor broke in it. Actually, no, I take that back. Is this the wash? Yeah, it was an old washing machine motor. So this was the motor that actually makes the water leave the washing machine. And what do you see around here? These are coils of wire. Coils of wire wrapped around these iron cores in my washing machine. Well, they did that because when you put AC current through it, which is what you get out of a wall, and you have, this is actually a magnet, this is the propeller, there's actually a magnet attached to the propeller, and the current would actually create magnetic fields that change, and it would cause this magnet here to spin, creating this pump action. If I had all the pieces together here, this spinning here would actually be the thing that pumped the water out. So the discovery of magnetic fields being created by wire, and then being strengthened by coils of wire, and then directed that way. There's a north on one side of the coil and a south on the other, depending on which direction the current is flowing. That discovery allowed us to create things like electric motors that, of course, are incredibly useful. Anytime you hear something that's plugged into a wall that's vibrating or pumping or something like that, like your fan, any water pumps, anything like that, they are using this technology, this method to do that. Okay, I'm going to do one more video. I'm going to end this video on that note and see you in the next video.